Welcome friends. In this session we discuss the relation between basis for a finite dimensional vector space V and the basis for its dual space V star. We shall answer a question about dual basis, whether every basis for V star is the dual of some basis for V. One way to answer this question is to consider V double star, the dual space of V star. In this session, along with the discussion of double dual space, the concept of annihilator of a subset and the notion of hyperspace shall be described. We shall also discuss the adjoint of a linear transformation. Dual of a dual space. We first see that if alpha is a vector in the vector space V over the field F, then alpha induces a linear functional L alpha on V star defined by L alpha of F equal to F of alpha for F in V star. For C belongs to F and F g belongs to V star, L alpha of C into F plus g equal to C into F plus g of alpha equal to C into F of alpha plus g of alpha equal to C into F of alpha plus g of alpha equal to C into L alpha of F plus L alpha of g. Hence, L alpha is a linear functional. We also see that if V is finite dimensional and alpha not equal to 0, then L alpha not equal to 0. In other words, there exists a linear functional f such that f of alpha not equal to 0. For the verification of the same, we choose an ordered basis B equal to alpha 1 etc. alpha n for V such that alpha 1 equal to alpha, and let f be the linear functional which assigns to each vector in V its coordinates in the ordered basis B. Then in particular f of alpha equal to 1. So that L alpha of f equal to f of alpha equal to 1 not equal to 0. Theorem 1, let V be a finite dimensional vector space over the field F. For each vector alpha in V, define L alpha of f equal to f of alpha, f belongs to V star. The mapping alpha to L alpha is then an isomorphism of V onto V double star. Proof. By the discussion given just before the statement of the theorem, for each alpha the function L alpha is linear. Suppose alpha and beta are in V and C is in F, and let gamma equal to C into alpha plus beta. Then for each f in V star, L gamma of f equal to f of gamma equal to f of C into alpha plus beta equal to C into f of alpha plus f of beta equal to C into L alpha of f plus L beta of f, and so L gamma equal to C L alpha plus L beta. Hence, the mapping alpha to L alpha is a linear transformation from V into V double star. Also, L alpha equal to 0 if and only if L alpha of f equal to 0 for all f belongs to V star, if and only if f of alpha equal to 0 for all f belongs to V star, if and only if alpha equal to 0. Hence, the transformation alpha to L alpha is non-singular, since dimension of V double star equal to dimension of V star into dimension of f equal to dimension of V star equal to dimension of V into dimension of f equal to dimension of V. The fact that alpha to L alpha is a non-singular linear transformation from V into V double star implies this transformation is invertible and is therefore an isomorphism of V onto V double star. This completes the proof of the theorem. The following result follows immediately. Corollary 1, let V be a finite dimensional vector space over the field F. If L is a linear functional on the dual space V star of V, then there is a unique vector alpha in V such that L of f equal to f of alpha for every f in V star. We are now ready to answer the question whether every basis for V star is the dual of some basis for V. Corollary 2, let V be a finite dimensional vector space over the field F. Each basis for V star is the dual of some basis for V. Proof. Let B star equal to f1 etc. fn be a basis for V star, then there is a basis L1 etc. Ln for V double star such that Li of fj equal to delta ij. Using corollary 1, for each I there is a vector alpha I in V such that Li of f equal to f of alpha I for every f in V star. That is such that Li equal to L alpha I. It follows immediately that alpha 1 etc. alpha n is a basis for V and that B star is the dual of this basis. This completes the proof. In view of theorem 1, we usually identify alpha with L alpha and say that V is the dual space of V star, or that the spaces V, V star are naturally in duality with one another. Each is the dual space of the other. Remark: V and V double star are structurally the same, that is, we can identify V with V double star, or we can put V in place of V double star, or a subspace of V can be identified with the corresponding subspace of V double star. The annihilator of a set. We recall that if V is a vector space over the field F and S is a subset of V, the annihilator of S is the set S naught of linear functionals f on V such that f of alpha equal to 0 for every alpha in S. If E is a subset of V star, then the annihilator E naught is the set of linear functionals L on V star such that L of f equal to 0 for every f in E. Thus, E naught is a subset of V double star. If we choose to identify V and V double star as in theorem 1, then E naught is a subspace of V, namely the set of all alpha in V such that f of alpha equal to 0 for all f in E. We note that each subspace W is determined by its annihilator W naught. How is it determined? The answer is that W is the subspace annihilated by all f in W naught, that is, the intersection of the null spaces of all f in W naught. In our present notation for annihilators, we have W equal to W naught naught. Theorem 2. If S is any subset of a finite dimensional vector space V, then S naught naught is the subspace spanned by S. That is, if W is the subspace spanned by S, then W equal to S naught naught. Proof: let W be the subspace spanned by S, then clearly W naught equal to S naught. Hence, W naught naught equal to S naught naught. Therefore, what we are to prove is that W equal to W naught naught. In the discussion just above the statement of the theorem, we have proved this. Another proof of W equal to W naught naught is the following. We recall that dimension of W plus dimension of W naught equal to dimension of V. Also, dimension of W naught plus dimension of W double naught equal to dimension of V star. And since dimension of V equal to dimension of V star, we have dimension of W plus dimension of W naught equal to dimension of W naught plus dimension of W double naught. So, that dimension of W equal to dimension of W double naught. Since W is a subspace of W double naught, in the sense of isomorphism, we see that W equal to W double naught. Hyperspaces. Definition 1. If V is a vector space, a hyperspace in V is a maximal proper subspace of V. Remark: if dimension of V equal to n, then the dimension of its hyperspace is n minus 1, that is, one short of the dimension of the original space. Theorem 3. If f is a non-zero linear functional on the vector space V, then the null space of f is a hyperspace in V. Conversely, every hyperspace in V is the null space of a not unique non-zero linear functional on V. Proof: let f be a non-zero linear functional on V and n f its null space. Let alpha be a vector in V which is not in n f. That is a vector such that f of alpha not equal to 0. We will show that every vector in V is in the subspace spanned by n f and alpha. That subspace consists of all vectors gamma plus c into alpha, gamma in n f, c in f. Let beta be in V. Noting that f of alpha not equal to 0, we define c equal to f of beta by f of alpha. Then the vector gamma equal to beta minus c into alpha is in n f, since f of gamma equal to f of beta minus c into alpha equal to f of beta minus c into f of alpha equal to 0. So, beta is in the subspace spanned by n f and alpha, hence n f is a hyperspace in V. Now, let n be a hyperspace in V. Fix some vector alpha which is not in n. Since n is a maximal proper subspace, the subspace spanned by n and alpha is the entire space V. Hence, each vector beta in V has the form beta equal to gamma plus c into alpha, gamma in n, c in f. We now show that the vector gamma and the scalar c are uniquely determined by beta. If beta has the representations beta equal to gamma plus c into alpha, gamma in n, c in f, and beta equal to gamma dash plus c dash alpha, gamma dash in n, c dash in f, then c dash minus c into alpha equal to gamma minus gamma dash. If c dash minus c not equal to 0, then alpha equal to 1 by c dash minus c into gamma minus gamma dash belongs to n, which is a contradiction. Thus, c dash equal to c and gamma equal to gamma dash. We conclude that if beta is in V, there is a unique scalar c such that beta minus c into alpha is in n. We denote that scalar by g of beta. Then it can be easily seen that g is a linear functional on V and that n is the null space of G. This completes the proof of the theorem. Lemma: if f and g are linear functionals of a vector space V, then G is a scalar multiple of f. If and only if the null space of G contains the null space of f, that is, if and only if f of alpha equal to 0 implies g of alpha equal to 0. Proof: if f equal to 0, then g equal to 0 and g is trivially a scalar multiple of f. Suppose f not equal to 0, so that the null space Nf is a hyperspace in V. Choose some vector alpha in V with f of alpha not equal to 0 and let c equal to g of alpha by f of alpha. The linear functional h equal to g minus c into f is 0 on Nf, since both f and g are 0 there, and h of alpha equal to g of alpha minus c into f of alpha equal to 0. Thus, h is 0 on the subspace spanned by Nf and alpha, and that subspace is V. Hence, we conclude that h equal to 0, that is g equal to c into f. This completes the proof of the theorem. Theorem 4, that g, f1 etc. f r be linear functionals on a vector space V with respective null spaces n, n1 etc. n r. Then G is a linear combination of f1 etc. f r if and only if n contains the intersection n1 intersection etc. intersection n r. Proof: if G equal to C1 into f1 plus etc. plus Cr into fr and fi of alpha equal to 0 for each I, then clearly G of alpha equal to 0. Therefore, n contains n1 intersection etc. nr. Now, we prove the converse by induction on the number r. By the preceding lemma, the case r equal to 1 is true. As induction argument, suppose the result is true for r equal to k minus 1 and let f1 etc. fk be linear functionals with null spaces n1 etc. nk such that n1 intersection etc. intersection nk is contained in n, the null space of G. Let G dash f1 dash etc. fk minus 1 dash be the restrictions of G f1 etc. fk minus 1 to the subspace nk. Then G dash f1 dash etc. fk minus 1 dash are linear functionals on the vector space nk. Also, if alpha is a vector in nk and fi dash of alpha equal to 0, I equal to 1 etc. k minus 1, then alpha is in n1 intersection etc. intersection nk, and so G dash of alpha equal to 0. By the induction hypothesis, there are scalars Ci such that G dash equal to C1 into f1 dash plus etc. plus Ck minus 1 fk minus 1 dash. Take h equal to G minus sigma I equal to 1 to k minus 1 Ci into fi, equation number 1. Then h is a linear functional on V, and using equation 1 we have for every alpha in nk, h of alpha equal to g of alpha minus sigma I equal to 1 to k minus 1 Ci into fi of alpha equal to g dash of alpha minus sigma I equal to 1 to k minus 1 Ci into fi dash of alpha equal to 0. By the preceding lemma, h is a scalar multiple of fk. If h equal to ck into fk, then g equal to sigma I equal to 1 to k Ci into fi. This completes the proof. The adjoint of a linear transformation. Suppose V and W be two vector spaces over the field F, and T is a linear transformation from V into W, then we shall see that T induces a linear transformation from W star into V star. Theorem 5. Let V and W be vector spaces over the field F. for each linear transformation T from V into W, there is a unique linear transformation T T from W star into V star such that T T G of alpha equal to G of T of alpha for every G in W star and alpha in V. Proof. Suppose G is a linear functional on W and let f of alpha is equal to G of T alpha, equation 2, for each alpha in V. Then equation 2 defines a function f from V into F, namely the composition of T, a function from V into W, with G, a function from W into F. Since both T and G are linear, F is linear, that is F is a linear functional on V. Thus, T provides us with a rule T T which associates with each linear functional G on W a linear functional F equal to T T G on V, defined by equation 2. We now claim that T T is a linear transformation from W star into V star. To prove this, let G1 and G2 be in W star and C is a scalar. Then T T of C into G1 plus G2 of alpha is equal to C into G1 plus G2 of T alpha equal to C G1 of T alpha plus G2 of T alpha equal to C into T T of G1 of alpha plus T T of G2 of alpha. Hence, T T of C into G1 plus G2 equal to C into T T of G1 plus T T of G2. This completes the proof. We call T T the transpose T or the adjoint of T. Theorem 6. Let V and W be vector spaces over the field F and let T be a linear transformation from V into W. The null space of T T is the annihilator of the range of T. If V and W are finite dimensional, then rank of T T equal to rank of T. The range of T T is the annihilator of the null space of T. Proof. If G is in W star, then by definition T T G of alpha is equal to G of T alpha for each alpha in V. The statement that G is in the null space of T T means that G of T alpha equal to 0 for every alpha in V. Thus, the null space of T T is precisely the annihilator of the range of T. Suppose that V and W are finite dimensional, say dimension of V equal to n and dimension of W equal to m. Proof of 1. Let R be the rank of T, that is the dimension of the range of T. Then the annihilator of the range of T has dimension m minus r. By the first statement of this theorem, the nullity of T T must be m minus r. But then, since T T is a linear transformation on an m dimensional space, the rank of T T is m minus r equal to r, and so T and T T have the same rank. Proof of 2. Let n be the null space of T. Every functional in the range of T T is in the annihilator of n. For suppose f equal to T T G for some G in W star, then if alpha is in n, f of alpha is equal to T T G of alpha equal to G of T alpha equal to G of 0 equal to 0. Now, the range of T T is a subspace of the space n naught and dimension of n naught equal to n minus dimension of n equal to rank of T equal to rank of T transpose. So, that the range of T T must be exactly n naught. Theorem 7. Let V and W be finite dimensional vector spaces over the field F. Let B be an ordered basis for V with a dual basis B star, and let B dash be an ordered basis for W with a dual basis B dash star. Let T be a linear transformation from V into W. Let A be the matrix of T relative to B dash, and let B dash be the matrix of T T relative to B dash star B star. Then Bij equal to Hij. Proof. Let B equal to alpha 1 etc. alpha n, B dash equal to beta 1 etc. beta m. B star is equal to f1 etc. fn, B dash star is equal to g1 etc. gm. By definition, T alpha j equal to sigma I equal to 1 to m a I j beta I j equal to 1 to n, T T g j is equal to sigma I equal to 1 to n b I j f I j equal to 1 to m. On the other hand, T T g j of alpha I equal to g j of T alpha I equal to g I of sigma k equal to 1 to m a k I beta k equal to sigma k equal to 1 to m a k I g j of beta k equal to sigma k equal to 1 to m a k I delta j k equal to a j I. For any linear functional f on V, f equal to sigma I equal to 1 to n f of alpha I into f I. If we apply this formula to the functional f equal to T T G j and use the fact that T T G j of alpha I equal to a j I, we obtain T T G j equal to sigma I equal to 1 to n a j I into f I, from which it immediately follows that b I j equal to a j I. Definition 2. If A is an m by n matrix over the field F, the transpose of A is the n by m matrix A T defined by A I j transpose equal to A j I. Theorem 7 states that if T is a linear transformation from V into W, the matrix of which in some pair of bases is A, then the transformation T T is represented in the dual pair of bases by the transpose matrix A T. Theorem 8. Let A be any m by n matrix over the field F, then the row rank of A is equal to the column rank of A. Proof. Let B be the standard ordered basis for F n and B dash the standard ordered basis for F m. Let T be the linear transformation from F n into F m such that the matrix of T relative to the pair B B dash is A. That is, T of x 1 etc. x n is equal to y 1 etc. y m, where y I equal to sigma j equal to 1 to n a I j x j. The column rank of A is the rank of the transformation T, because the range of T consists of all m tuples which are linear combinations of the column vectors of A. Relative to the dual basis B dash star and B star, the transpose mapping T T is represented by the matrix A T. Since the columns of A T are the rows of A, we see by the same reasoning that the row rank of A, the column rank of A T is equal to rank of T T. By theorem 6, T and T T have the same rank, and hence the row rank of A is equal to the column rank of A. This completes the proof. Remark in view of theorem 8, if A is an m by n matrix over F and T is the linear transformation from F n into F m defined above, then rank T equal to row rank of A equal to column rank of A, and this number is called the rank of A. Now, let us summarize the session. In this session, we have discussed the relation between basis for a finite dimensional vector space V and the basis for its dual space V star, the concept of annihilator of a subset, and the notion of hyperspace have been described. We also have discussed the adjoint of a linear transformation. Before we attend the next unit, please try to answer the following questions. 1. Let W be a subspace of a finite dimensional vector space V and G1 etc. Gr be any basis for W naught. Prove that W equal to intersection I equal to 1 to R n Gi. 2. For a linear transformation T from V to W, describe the dual T star from W star to V star. Show that rank of T equal to rank of T star. 3. Let V be the vector space of all polynomial functions over the field of real numbers. Let A and B be fixed real numbers, and let F be the linear functional on V defined by f of p equal to integral a to b p of x dx. If D is the differentiation operator on V, what is D transpose of F? 4. Let V be a finite dimensional vector space over the field F and let T be a linear operator on V. Let C be a scalar, and suppose there is a non-zero vector alpha in V such that T alpha equal to C into alpha. Prove that there is a non-zero linear functional F on V such that T T F is equal to C into F. Hope you enjoyed the session. See you next time. Until then, goodbye.